to this computer. Okay, I am now recording. All right, class. Today we're going to be covering two topics. The first being taking unstructured data and converting it into a format for which we can now derive information. And the second is a set of pattern matching technologies called regex, which is actually what Zemo and Justin covered in their presentation today, as well as some of the NLTK things that they touched on. This class will lead us into next class when we talk about sentiment analysis. And beyond that, today we're really just focusing on how to take something that's very ambiguous, very, abstract, and applying a structure to it so that we are able to derive patterns, derive information, derive counts, derive summary statistics, so that at the end of the day, you can actually analyze unstructured data by applying structure to it. So that's really the goal of today's lecture. Obviously, as we go along, if you have any questions, you may interrupt me or you may put it in the group chat. If you hear my dog in the background, his name is Watson, and he's currently barking. So what is unstructured data? It's everything that is not included in structured and semi-structured data. Another way to put that is free text. Another way to consider this is non-delimited file formats. So a delimited file format would be something like a CSV or a JSON file where you have keys, values, or separators. A non-delimited file is something that doesn't separate one piece of information from another. It's all together, mixed in without a reasonable way to distinguish one piece of information from another. And the reason that it's unstructured either has to do with the nature of the way that it was collected. So for instance, log files, or it has to do with let's say, not being generated by a machine. A good example might be a Word document. It might be it might be a tweet. These are both examples of unstructured data, and the reason they're unstructured is because it's just text. It's just someone writing, English or Hindi or Chinese. All of these are considered just unstructured data. Okay, so like Group 11, we're going to talk a little bit about NLTK, but we're going to focus specifically today on text tokenization. So we're going to be using the NLTK library to achieve this, but tokenization is the following activity. It's separating a group of text typically on some separator. The separator can either be a space or a punctuation mark into a list of specifically analyzable units of analysis. That could either be single words, groups of words, such as sentences. They can also be, things called bigrams, which are two-word sequences. So for instance, let's take the first sentence. There are many examples of data where all or part of the data is a text. An example of a bigram would be the combination of there are, combination of are many, combination of many examples, combination of examples of. A trigram would be something there are many examples of. And by separating and grouping the text into these units of measure or units of analysis, we can actually learn and derive new patterns of language, which is ultimately the purpose of natural language processing. It's to derive insight from inputs that are not structured. And from there, you can do things like sentiment analysis or identifying the mood, the tone, the directionality of the language imputed into text. Okay, so to start it off, we're going to import NLTK. NLTK is a package available to you all through the Anaconda distribution, so you shouldn't have to do any installation. And as Justin and Zemo said, NLTK stands for Natural Language Toolkit. Okay, from NLTK, the first step is to do nltk.download open close paren. It's going to launch a window. Now this window is going to allow you to download particular packages associated with the NLTK library. The reason that we're doing this is because there are what are called corpuses or libraries, or in this case, we're going to actually download the one called book. and it's a series of files that we're going to use as reference material when doing things like language analysis. So specifically for this class, the collection that you'll need is the one called book. So if you actually take book and double click it, it will install or download the collection called book. This will be used for information that we'll use as a stop word library. And we'll learn a little bit about stop words in a bit, but stop words are common English words that are generally not important with respect to analysis. Yes, there is a question from Rohan. Rohan, what is your question? Never mind, there may not be a question from Rohan, okay? So from here, we've downloaded the NLTK package, and I just realized it's getting kind of dark in my room. So hold that thought, I'm gonna turn a light on. Okay, I'm back. So now that we've downloaded the book program, I'm sorry, the book library for the NLTK package, we'll now be able to access the information within book, but we're not gonna get there quite yet. So, the first question is, and this might seem like a silly one, but what do we define as a word? If you define word from a dictionary, it's a single, I don't even know. I actually don't know the English language definition of a word. Let's Google it. Define word. A single, distinct, meaningful element of speech or writing. Okay, let's use that as our definition when we want to analyze what is a word. And the reason that it can be tricky is, number one, does a word include end punctuation? Does it include proper nouns? Does it include contractions, as we have in English? Does it include numbers or time? And what about things like hyphenated words? Are these all considered words? Are these conjoined words? The definition of word may not be as simple as you might think. So, because of the difficulties in the definition of what a word is, we're going to actually do a couple of different things in preparing or cleaning our data before we're able to analyze. So here we have a big block of text. We're going to save it as a string. Some of them are words, some of them are characters, but ultimately it is just considered a chunk of text, nothing more, nothing less. From there, strings have a method called .split, and by default, it will split on spaces. So here, you can actually indicate what you want to split on, but it will say return a list of the words in the string using sep as the delimiter string. So here, sep by default is white space. So not just spaces, but any white space. It'd be tab, new line, or a space. And that's what will split or differentiate one word from another. So using the string method split, we ended up with a list of what it considers to be unique character strings separated by white space. So some of these are tricky though, right? Aisle, again with exclamation points. 6:25 p.m. Are they really words? Kind of. Some of them are, certainly. Here we have just a hyphen. Okay? So we can see that this doesn't always work, and punctuation can certainly act as a challenge here. So for instance, if we wanted to know the number of instances of the word gate, is gate with a period equivalent to gate without a period? It's not. And programmatically, it would be challenging to count the number of instances of gate without first removing that period. So we need smart, intelligent ways of getting around this type of problem. So not only does text have words, but punctuations, number, and other special characters. We want to separate. We want the separation to include those as well. So instead of just splitting on white space, we actually want to split on things like periods, exclamation points, apostrophes, hyphens. So to do that, we're going to use the NLTK word tokenizer. And it's going to be using that library that we downloaded earlier, the one called book. It's going to use the words in the book. to define what is a word and what gets separated out. So this tokenization process yields what is called a token. Token is just a unit of analysis in natural language processing. And here we're going to word tokenize on text. So again, this is our text block here. We're going to word tokenize that block of text. Now you'll notice that we now have I apostrophe LL, so it's slightly different. We've parsed out the punctuation into their own character sets within the list. So particularly I and won't or wouldn't have now been parsed out. And let's make the text, we can do some frequency analysis now. So specifically, we can just write a quick program to do a frequency check. So we have tokens here, and then we'll do unique. We'll create an empty dictionary. And then so for word in tokens, if word in unique dot keys, then we'll do unique word plus equals 1, else we'll do equals 1. Print unique. Okay, so this is actually going to print the number of unique instances of all of the words in that text. So for instance, to occurs twice, at occurs twice, exclamation occurs twice, and then let's say we want this to be sorted. We could do something along the lines of, I'm actually not going to go down that route because it's going to take a little bit of debugging for me to get there. But you get the idea. So this is just a quick way to get frequency counts. And there's probably even a better, more succinct way than my quick for loop here. Okay. So from, by the way, we're going to touch on some of the stuff we did last time regarding Twitter. Now, if you have not gone ahead and created a Twitter API account and all of those things, don't worry, you can still follow along by picking up here. So I attached something called tweets.csv. You're going to get you're going to get very similar tweets to what I have here. So I ran this morning, creating this file. Everything that I'm doing up until that point is just fetching the data from the internet. So here I'm going to be importing TweetPy and JSON. I'm also going to be importing my YAML file. YAML file has my my configurations to Twitter, and I didn't want to share that with you all, so I have it living in a YAML file, which is just a semi-structured data format for configurations. I'm then making a connection to the Twitter API. From there, I'm actually going to query Delta, getting 150 Delta tweets just to make sure that my connection is set up. Delta is an airline, by the way, in case you did not know. I have 150 Delta tweets. Here's what they look like. The most recent one, here's your bag refund request. You can submit a refund request by clicking on this link. Somebody complained and they probably responded to them. Caring for you is our top priority. And the third one, the bag has made it to NLAN and still waiting to be loaded. Okay, it's very nice that they're doing this over Twitter. Seems a little personal. So for our analysis today, though, we're actually going to be considering IBM Watson's Twitter account, so at IBM Watson. And that's also the tweets.csv that you have available to you on Blackboard. So I'm going to grab 500 tweets from IBM Watson. You can see them here. So here are the most recent 500 tweets from their timeline. Humbled to step into the role of IBM CEO, sharing my letter to the IBMers today. Okay, perhaps there's a new CEO at IBM. That's news to me. Okay, as a CEO of IBM, avid learner and listener, relentlessly focused on what's next. Okay, I'm actually now intrigued. Does IBM have a new CEO? Oh, I probably should type it in right. IBM. Yes, as of today, we have a new CEO of IBM. Okay, so that's why we are tweeting specifically about this new CEO. Good timing. I think our tweets will be very, very specific to this new event. Okay, so now we have the most recent 500 tweets by the IBM Watson account. Okay, the next thing I'm going to do is I'm going to establish my connection to MongoDB. That means that for those of you following along, you do need to do MongoD to instantiate the Mongo database server on your local machine, which I've already done ahead of time. Okay, so once I have my my connection, I'm going to create a database called client.tweets. Within that database, I'm going to create a collection called Watson Timeline, and I'm going to take those 500 tweets and load it to MongoDB. Now, why I'm doing this is just a reminder of that workflow and what we've seen in the past. From there, I'm actually going to then export all of those tweets back into an object called docs. So docs is just the set of all of those tweets with the metadata associated with it. And then from there, I'm creating a document, and that document is available to you. It has 700 because I think I loaded 200 tweets earlier today. That's the reason it doesn't say 500. So picking up where we all left off, I'm now ingesting the thing called tweets, CSV. This should be the same file that you all have available to you on Blackboard. Okay. 500 tweets, give or take 200. Let's actually see how many do we have. Oh, I have 700. Nevertheless, I think the analysis will still work. So now that we have a list of tweets, we want to actually tokenize this. So we want to separate each of the individual words into an element in a list so that we can analyze it. Okay, just a reminder how to tokenize. So what it's done here is the first element in tweet list, we've grabbed that tweet. Okay, so from tweet list 0 to combat bullying, Watson app teamed up with IBM to create AI solution. So we've parsed this into to combat bullying, Watson app teamed up with at IBM. So we've tokenized. However, we want to actually now run and iterate through all of the tweets, tokenizing each one of them and adding them to a single list. So we're actually going to create this list comprehension, which iterates twice. So first of all, token for tweet in tweet list, for token in NLTK word tokenizer. So effectively what we're going to do is for every element in the token, for every element in the tweet list, we're going to tokenize it. But for every token in that outputted token list, we're going to add it to the final list. So instead of getting a list of lists, we're going to get just flat a single list of all words in all tweets. So you'll notice that the old tweet ended here. The next tweet immediately runs into the same list. So all of the words from all of the tweets are now in a single list. I just want to point that out because that is non-trivial because we're doing effectively a double list comprehension here. Token for tweet in tweet list for token in NLTK.word tokenizer tweet. It's a mouthful. Okay? And the len, this is how many unique tokens we have now, i.e. unique words. 17,323. Okay? We can now make a word frequency dictionary ourselves, sorted in reverse frequency order, and we can do that instead of just writing a for loop. There is such thing as NLTK.freqdist, or frequency distribution. You pass in all of the tokens, and then we can just show the 30 most common. So here, the 30 most common aren't very helpful though, right? Colon, @ HTTPS, comma, the, hashtag, to, dot. AI is the first one that's even remotely relevant, then IBM, then Watson. So among the 30, only about 4 are actually of any use, right? So we haven't actually really learned anything at this point. It wouldn't be helpful to train a machine learning model on this data. It wouldn't be helpful to do sentiment, nor would it be helpful for classification or clustering. So how do we get rid of all the noise? And that's what we're going to do next. So before we do that, though, you'll also realize that many of the words are capital and some of the words are lowercase. Python is capitalization specific, as you well know. So how do we overcome the problem of frequency distribution when some are lowercase and some are uppercase? As a best practice, we make everything lowercase when we do these types of analyses. So here, toke.lower for tweet and token list for nltk.word tokenized. So our double list comprehension, we're going to go a step further and actually cast it as the lowercase version of itself. So it's all those same tokens that we had earlier, the 17,000 whatever, but everything here is now lowercase, including AI, including proper nouns like IBM. This way we can guarantee that, let's say, human capital and human lowercase are the same word when we do frequency distributions. Okay, so that was the first data cleansing step, casting everything as lowercase so that we have a unified set of information that's analyzable. Okay, so this is the entire token list of lowercase words and their frequency distribution. The next step that we're going to implement is removing what are known as stop words. Stop words are words which are filtered out before or after processing of natural language data, and usually they represent typical non-informative words. Things like the, at, my, his, hers, that, this, those, they. They're not verbs and they're not nouns. They're sort of the connective tissue of everything else. They're not overtly informative in and of themselves. So in order to use this, in order to remove stop words, we're actually going to import stop words using nlp.corpus.stopwords words in English. There are certainly words in other languages as well, so you can take a look at what other words are available to be used. But here we're going to use the English stop word dictionary. Okay, there are 179 stop words, and here are the first 25. I, me, myself, we, our, ours, ourselves, you, your, you, you'd, yours, yourself, he, him, his, himself, she, she's, her, herself. That was recorded, so that was it's going to be a fun thing to rewatch. So now that we have a set of stop words, we're going to go ahead and remove these. The reason that we're removing them is because they don't provide us any analytical value. These are just, I can't think of the part of speech that these represent, but they are non-informative words that we don't need in our analysis. So this list is also meant to be applied to lowercase words. As you can see, even I, which is always uppercase, is lowercase in this sense, because the best practice is always to compare lowercase words when doing natural language processing. So regarding all of those stop words, we're going to go a step further in our tokenization, and we're going to say if the token is not in NLTK stop words. So only give me tokens that are not stop words is really what we're saying here. So here are some tokens that are not stop words. And actually we can take the length of this. Well, so remember we started with, I think, 17,000. Now we're going down to 12,000. Let's see if I can get that number really quickly. Yeah, it went from 17,323 to 12. So we lost about 5,000 words, or roughly, I don't know, 27% of the words here. Okay. So we still need to remove punctuation. We don't really care about analyzing periods, commas, exclamation points, pipes, tilde, ellipses. So we're going to have to do a little regular expression analysis, the same way that Zemo and Justin did to analyze email domains. We're going to use regex to actually pull out particular parts of speech pertaining to punctuation. So we're going to cover more about regular expression and pattern matching in about 25 minutes. But for now, just assume that we're creating a filter which will pass a true or a false, indicating whether or not the entirety of a string block is nothing but punctuation marks or non-alphanumeric characters. If it's all alphanumeric characters, then it's true. If it's not, then it's false. So pattern match a word of all it will be true if it's nothing but alphanumerics. It's false if there are alphanumeric characters, i.e. ABC through Z, 1 through 9. Okay, so to remove words that have all non-alphanumeric characters, we're going to do not, and then apply this function, alphanumeric character, which yields a true or a false statement. All right, we are now left only with alphanumeric words that may have punctuation, but we are not left with any commas, spaces, ellipses, etc. as unique elements of the list. Okay, so now that we're left with mostly just words, now we can start to do more informative analyses regarding frequency. So for instance, HTTPS, still not that informative, is the most common. AI is the second most common with 271 instances. IBM third with 224. RT, which is short for retweet. Let's see if we have data at 66 instances. Learn, 64. Technology, 37. So this is just like a little bit about the types of analysis that you can do regarding frequency of single valued tokens. Okay. Now note, if you're specifically going to analyze Twitter, beyond the English tokenizer that we used, you could also use specifically a Twitter tokenizer. So here, we're going to call it T tokenizer, and it's nltk.tokenize.tweet tokenizer. So now we can actually use the Twitter tokenizer to yield things that are more Twitter related. So handles, so at and name, hashtags for categorized data. If we use the English tokenizer, these would be separated into separate characters and separate words. But if you wanted to incorporate tweets that use the tweet stuff, you'd want to use the tweet tokenizer from NLTK. Okay, so we're going to do the same analysis that we ran through earlier. So we're left with specifically pound AI or hashtag AI, hashtag IBM Watson, at Rob Thomas. Rob Thomas, by the way, he is not the musician Rob Thomas. He is the head of IBM Watson. So his handle is one of the most frequent parts of a tweet from IBM Watson. Okay. Now, so far we've only looked at single instances of tokens. Now we're going to look at bigrams. Bigrams, as I mentioned, are two-word associations for analysis. And it's nice to look at these because it can be a little bit more informative than just single words. It can sort of show intention. It can show adjective-noun pairs. It can show noun-verb pairs. And by doing bigrams and trigrams, you can learn a little bit more about sentiment. So here, what we're doing is we're taking those same tweets and we're combining them. So to combat bullying, comma, Watson app teamed up with at IBM. So by combining two words at a time, you get a little bit more intentionality with respect to the data set. Okay. What else do we have here? So to actually use bigrams and to do different analyses, we're going to do nltk.collocations, import all things from collocations. Okay. We're going to use the bigram collocations, bigram associative measures. So these are different statistics or metrics that people use in measuring bigrams. For instance, we can actually determine the frequency or the percentage occurrence among all bigrams of specific bigrams. So for instance, the most frequent combination of two letters is in the. Similarly, of the, and then retweet at IBM. So these are the three most common combination of letters based on the percentage of all bigrams. So for instance, this is in 0.25 or a quarter of a percentage of all bigrams are retweet at IBM. Okay. Forget where I was going here. So among all of the combinations. I think we touched on this a little earlier. We can see these scores and are sorted by the decreasing frequency. We did take a look at this already. So we'll filter out the special characters by using the alpha filter. Oh, now I remember. So we want to remove instances where we have nothing but, I lost my train of thought ever so slightly. Where was I going? Oh, we can use different filtering mechanisms to remove instances of characters or words or word combinations that we don't want. So here we're going to apply the word filter on the bigrams, alpha filter. So only give instances of where the entire word in the bigram are nothing but are not entirely characters which are composed of punctuation marks. So here, let's say just the @ symbol, that would get removed. From there, we also can do the same by saying, don't give me anything that has stop words. So we can actually filter out stop words here. So these are the bigrams that do not include stop words. So retweet out IBM, IBM Watson, natural language, Watson Assistant, customer service, language processing. Okay. Additional ways to filter bigrams. So another filter would be remove words that only occurred with a frequency over some minimum threshold. So here, let's assume we only want words that occur at least 5 times. Okay. So minimum frequency, apply a frequency filter, use the minimum frequency, and then only give me instances of words that have occurred at least 5 times in the entire data set. Similarly, only give me words that have occurred. Suppose that we want to filter out bigrams where the first word's length is less than or equal to 2. So we don't want short words. Like we don't want just AI. We don't want I, you, he, I, me, it. So here we take a lambda function across both elements of the bigram and we say where the first element of the bigram is less in length than 3. So these are just different ways that you can filter your bigrams for analysis and so that you can actually draw new conclusions about your data set. Okay, I'm going to take a quick pause. Do I want to go? No, I don't really want to go through that. Any questions regarding tokenization, filtering of data, stop words? I know I kind of went through this really quickly, but I just wanted to get a chance to get it in front of you before anyone needed to duck out at 8 o'clock. So we'll take 5 minutes. Are there any questions? I'm happy to go back and review anything. Okay. Gier asked, do we need to download a book every time we want to use this source code? No. It's a single download. It downloads a file, a physical file onto your computer, and then NLTK will reference that file forever until that file is deleted. Any other questions? Okay. I'm going to take I just need a 5-minute break. So I will kick off the second half of the lecture starting at 7:55. I can't believe it's that late already. So take 5 minutes, freshen up, and we'll get started back at 7:55. Okay, welcome back. Do we have any questions about anything? You can literally ask me any question you'd like. Not a single question. Okay, can you all hear me? I want to make sure you can still hear me. I feel like sometimes I don't know if you can hear me. Confirm. If we are doing other projects, are there some websites for people to find a awesome? Gier, I'm not sure I understand your question. Gier, can you ask your question in another way? Oh, positive and negative word list. Positive and negative, something like hat. I still don't quite understand. Do you want to maybe, if you unmute yourself, it may be easier to articulate it over audio.
Sorry for the confusion. I just want to ask, like, when we are doing sentiment analysis, right? We need a list of words that maybe contains positive words or negative words.
Sure.
And where do we find those kind of like a list of words that we can use?
Good question. So first of all, we're going to do sentiment analysis next week. But in terms of accessing lists of words, it really depends on, first of all, the domain. Positive and negative really is domain specific. If, for instance, you wanted to filter out, let's say, inappropriate language, negative words may be just simply curse words. But for instance, in certain, I don't know, under certain circumstances, curse words could also be used in a positive way. So I think positive and negative word lists probably exist based on your domain. You might be able to even fetch them from, just a website, and you could do something like a web crawl to fetch them from the website and then convert them to a list. Once you have the list of positive and negative words, you can just create a filter or a function that returns true or false based on whether or not it exists in that word list or not. But in terms of a general positive and negative, NLTK probably has a library of universally positive versus negative words, and we are going to touch on that next week.
Okay, thank you.
Sure. Okay. Any other questions? Any questions at all? So I think what I'm going to do is I'm going to briefly introduce regular expressions this week, and we can recover it again next week. It's a very dense topic, and it does require a keen eye and attention to detail to get right. I certainly think that there's a lot to be learned about regular expression, and you could probably take an entire semester's worth of material just to get it right. It's a very complex, and there's a lot of different ways to use the tool. It's also not Python specific. It is a general paradigm for pattern matching with respect to natural language. But today we are going to look through the most common use cases for regular expressions. And if you do have any questions about specific syntax, I would point you in the direction of the Python regex documentation or the tool that we're going to use in tandem today called regex pal. The reason being is that I am not the best regex user. So if there is a specific question about one syntax versus another, it would take me a little bit of debugging to get you there because it's such a dense library. But it's a really useful tool when you're doing free text parsing. And I definitely I want to introduce it today so that you're all familiar with it and have the ability to use it for things like your final project. So regular expression is also sometimes called regex or regex. And in Python, we're going to abbreviate it as RE. It's a notation for specifying patterns of text. Most modern programming languages like Python have packages that allow you to define patterns in regular expression notation and have functions that allow you to actually parse or match specific patterns out of free text. Now, a lot of websites like a lot of website technologies like JavaScript or even some sophisticated server applications also have regex functionality. So anything that we learn with respect to Python could be commuted to another programming language fairly easily. It all uses a very similar syntax. So we'll start by looking at some really simple examples of text matching examples. And then we can sort of jump into how it would be applicable to parsing information out of free text. So how do you match whether or not a word has a capital letter or maybe like an optional S to pluralize it at the end of the word? These are the types of questions that kind of come up when you would want to tackle regex. So here, the most simple example is the classifier, does a character contain a letter? So here, the regex pattern match is just the letter that you want to have. And then it's going to say, yes, Z exists in the index number 2, 0, 1, 2. Z is here in 2. It's the simplest example. Look for a single letter. Okay? Is there a question? Okay. A few more examples. What if we, and by the way, so the next type of example looks for a character, what's called a character class, or a set of character notations within square brackets. So here, the regex expression little w, capital W, is looking for a single lowercase or capital W. So for instance, it would capture, or it would find the lowercase w in woodchuck and the uppercase w in woodchuck separately, or it would find an instance of one or the other. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 matches one of these digits, one of any of them. So it matches any of these instances. 0 through 9 is an abbreviation of the same numerics 1 through 9 above. A-Z is any capitalized letter within the alphanumeric character set. Any lowercase letter within the alphanumeric character set is square bracket lowercase a through z. And we're going to actually use a tool called regex pal to better understand how this would work. So let's just jump in there really quickly. So I'm going to put a piece of text. I'm going to write, it's getting late. Ben's class is running until 8:30 p.m. Monday night. Okay, so now in this regular expression block, we can just pass any regular expression notation. So here, give me instances of anything that has a lowercase w or an uppercase w. So note, this isn't anything in square brackets is optional. So if you have a lowercase w or an uppercase w, highlight it below. So the capital W's are getting highlighted. Similarly, highlight anything capital A through Z. It's going to highlight all of the capitalized letters. or capitalize, or give me all letters lowercase a through z. It's going to give me all lowercase letters. Additionally, if you want to give me all of the periods, in that case, you actually don't need, I'm sorry, you do need square brackets if you want the period character. Period character without the square brackets, it's just any character whatsoever. So the only time this wouldn't return anything if it was an empty string. Okay. And if specifically I wanted bends, this is going to give me any character that is capital B, E, N, apostrophe, or S. Note that it's an or, it's a character set, it's not a discrete word. If you wanted bends specifically, you would not use the square bracket. Okay? So neither is just, it's like the not statement. So this is, it takes the opposite of what we're looking for. So give me anything that's not bends. Give me anything that's not B through E and S. It has to go on the inside. This relates to character sets. So this is going to say, give me anything that's not a capital B, E, N, apostrophe, or S. Okay. If you want specific or words, you can do, let's say, give me Monday or give me running. Matches any words, groundhog or groundhog. We can do that one as well. So let's say, so this is going to give me Monday or running, even if Monday is lowercase or running is capitalized. Capitalized at the beginning of the word. So the question mark is an important one. The previous letter is optional. So here, color can be either spelled like the British way, C-O-L-O-U-R, or the American way, C-O-L-O-R. So there's a lot of different ways that you can kind of play with regex. Again, I implore you to take a look at the documentation. There's a lot in here, and there's sort of like the way that we had to parse out the date time format using the Python strip time. I find that regex is similarly particular about syntax. So I really recommend that you do your research in the documentation. So there's more examples of different regex characters, but we're going to just skip ahead and start to play with regex in real life. So first you're going to import RE. That's short for the Python regex package. Okay. The next thing is if you want to actually instantiate a particular pattern, you're going to do compile. So it's the pattern is equal to re.compile regex syntax. So the regex syntax is the exact same one that you've been using in the regex pal up here, compiled as a parser. Now it's going to return, depending on the way that you're going to implement it, it's either going to return a Boolean, true or false, or it's going to return where in a character set your pattern has been matched. So let's imagine we have the text, pound, that book is interesting. So we're going to match this regex character set, which, by the way, is any character, not punctuation. Any alphanumeric character, not punctuation. Okay, so functions to use a regular expression include the match function to return a matched object. And the match object from the function match will return true if the pattern matches at the beginning of the text, false if not, so the beginning of the text. You can also do a search. So it's match or search. Search will return true if the pattern matches anywhere in the text. So again, match is the beginning of the text, search is anywhere in the text. And it's really important because it'll give you different answers. So specifically, that word is interesting. This is going to tell me, is the beginning of this phrase an alphanumeric character? No. If it prints nothing, that means it's false. So if, or we should actually just do the result. Of course. So it's printing no result. So that means it didn't find anything. The beginning of this is not an alphanumeric character. But if you search, are there any alphanumeric characters? That's the next question, right? Because we're using now the search function. Anywhere in the text, is there an alphanumeric character? Yes, there is. True. Okay. So from a match object result, so this is not search, this is match. From a match object result, there are functions to find strings that match. So match.group, match.start, match.end, and match.span. This is how we get the index location of where these matches are occurring. So returns the string matched by the regular expression. Okay, that's an important one. Returns the start position of where the match occurs. Returns the end position of the match. Returns a tuple containing both the start and the end. So for instance, if you wanted to take a subset of the string, you could look up based on a regex expression, getting the index of where it starts and ends, and then actually use that as your start and end string slice to get the string that you want, which is what we're going to do now. So we have pounds, 101 pounds. And here, this is saying, give me anything that's 0 through 9. Yes, give me any set of characters. Plus means repeated any number of times. So give me any repeated digits between 0 and 9 any number of times. So let's say that this was that. It would yield all of the digits in sequence up until pounds. That's what the plus operator is doing. And we can actually take a look at this in the regex testing. Okay. It's going to highlight any sequence of numbers. Because what we want to do is we want to separate the actual amount from pounds to convert it into something like a string. Okay, so here we're taking 101 pounds and we are matching where we can actually get just the number. So here we have the span. So from 0 to 3, 0, 1, 2, 3, non-inclusive. So 3 is a soft boundary. We get the digits 101. So if we actually did something like this would be the digit matched. Okay. Now we're just going to create a random set of integers, and we're going to take a look. It's in a series. So these are just random weights that we've created by rand int between 0 and 1,000. And then we've added the string LBS to the back of it. And we've done it for 100 random integers. So now we have a list of 100 characters, all of random weights between 0 and 1,000. So some of them are different lengths. And now we want to regex and fetch the start and end of all of that character set. What did I do here? What did I want to do? Random series, maybe? Yeah, nope. Oh, I did this earlier. Why isn't this working now? Oh, I created something before it was available. Gotta apply x.group. Ouch. Oh, I know why. Bear with me for a quick second. I realized that I made a mistake earlier. So it's x dot, and now it's compile, re dot compile. It's my regex expression. X. What did I do wrong? Cannot process flag argument. Ugh, okay. Apply lambda, compile. Oh, did I switch the order? Sorry, y'all. I'm just trying to troubleshoot my error in encoding this. I have the thing, and then I have the decomposition. I'm applying it via lambda. Where am I going wrong? Where am I going wrong? Can I process flags argument with a compiled pattern? Interesting. I did ilog 0, and then I did re.compile ilog 0. That should work. No, it doesn't work. Why doesn't it work? Pound search. I am missing something. Oh, it's re.match. I'm a fool, not compile. I'm sorry, y'all. Okay, there we go. Problem solved. Wrong method. Okay, great. So I've taken my series of 100 random pounds. I've then compiled based on identifying all of those integer instances. I then am now struggling again. Why is it struggling here? That's why. I'm then parsing and yielding only the matched text using x.group from my matched text. Similarly, I can do x.start, so it gives me the index start and index end, or index span over that character set. Now let's actually look at index span, because some of them are 0, 2. So instances where the weight is only, let's say, 27 pounds, the upper bound will actually be the second index, not the third index of many of the triple-digit weights. And also, if it was 1,000, it would be 0, 4, because it would be from the first digit all the way to the fourth digit. Okay. Whew. Now, this is very often, this is what we're looking for, right? We're looking for find all. It's a function that returns a list of results from that matches in a string. So for instance, if we want all of the, I don't know, emails from a big block of text, you want to parse through the text and just yield a list of emails, you're going to want something like find all. So here, let's take a look at short text for a minute. That book is interesting. Whoa. Give me all sets of characters that are alphanumeric, which is regex.findAll, the pattern here, so pattern, and the actual short text that you're parsing, and you end up with that book is interesting. Sort of the same tokenization product that we were looking at earlier using NLTK. Okay, now suppose you want to match all the numbers that can occur with commas and possibly a decimal point. on our first try, we might write the following regular expression. So there's a lot going on here. This is something like, take a look at the first 3 digits, then maybe it's a comma, and then 3 digits, and repeat that n number of times until you found all of the instances of 3 digits and commas and periods. So as a result, find all will only report the submatches that occur within the inner group of parentheses. Here. This is very convoluted, but instead of using find all, we're actually going to put an extra pair of parentheses, and I'll show you why that is. So let's imagine we have this text. The company had 13,299,100 shares of stock that was valued at 13 days at 4.5 points. Just a statement. Okay. If I want to fetch all of the all of the numeric characters with commas and periods, I get this result, which is not very good because it's only looking for the middle instance. So it's only looking for the final 3 following a comma. So here we only end up with 100 and the 0.5. Now, if we actually want this number, and this number, we wrap everything in an extra set of parentheses simply due to the syntax. So I'm not exactly sure how the syntax kind of breaks down in this instance. I think it's important. If you're struggling, it might have to do with the way that you've aligned your parentheses for the analysis. Okay, we also take a look at the result for each of the 3 options. So option number 1, option number 2, option number 3. Under option number 1, we find this character set. Option number 2, we find this character set. Option number 3, and we get this one. The combination of all 3, 13,299, 13, and 14.5. All right. Another useful function is that of substitution. So if we want to replace one word with another, my Uncle Fred has a red shirt. If you want to replace red with blue, and you end up with my Uncle F. Blue has a blue shirt. So it's actually a little bit of a trick there because Fred has the word red in it. But if it was, let's say, my Uncle Steve had a red shirt, now he has a blue shirt. So it's a useful function to have is the replace function. Okay. Another example is to remove leading or trailing white space. This is very common. So here, re.compile, leading and trailing white space. We have a tab here. I'm sorry, we have a couple commas here. We have a /n/t, which is line break tab. And we have just the text without the white space. Okay. So to round it off, we are now going to look at regular expression patterns in actual text data. So imagine we have a set of logs, and here's one line from the log. It's just kind of gibberish. It's a lot of nonsense. It might have some IP addresses, the date that it occurred, the HTTP call, here was a GET request, the machine that it occurred from, and the website that it was making the request to. So a lot of information here embedded, and it'd be really helpful to parse out each of those pieces of information, the type of call, the response, the server, the timestamp, all of those things. So maybe the first thing we want to do is extract the date by looking for the string inside square brackets. So note here, these are actual square brackets. That's the text that encodes the date. Why is that? Just the way that this particular log file is written. Has nothing to do with anything else other than the structure of this block of text. So here we have a regular expression which fetches all character sets embedded between square brackets. And this is an escape character so that it's representing square brackets as actual brackets, not as the encoding in regex. Okay, so it's grabbing all of the characters within the square brackets, and we're left with the date and a time zone. And since we've actually played with datetime formats in the past, that's something that you can actually convert to a Python datetime. Now, the next thing that we want to do is we want to suppose we want to find the server contents, which are being requested by the GET request. We can retrieve similar regex expression to find strings inside double quotes. So let's imagine we want everything that's within this double quote, this double quote, and this double quote. So find everything within double quotes, kind of like find everything between square brackets. So here, escape double quote, find any characters, any repeated n number of times, as long as it's not a backslash. I'm sorry, as long as it's not a, so give me any character that's not another double quote between another double quote. Okay, and we get 3 elements. We get, we get the dash, and we get the Mozilla stuff. And here's the first one, get robots. Okay, now you can actually get the actual server content request by selecting the part after the get request, but before the HTTP. So here, compile everything between get and HTTP, and you end up with robots.txt. So between get and HTTP. Now note some of these lines don't have get requests. So in these cases, we'll just get an empty string with dashes. Dash, 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 dash. As a reminder, we can convert that datetime format into Python datetime. And then finally, we can also look at an additional regular expression example of getting characters between square brackets or double quotes. So give me anything that lives between a square bracket or a double quote. And that's what we've done here. Okay, so this is playing with regular expressions. It's really great for parsing text. It's really helpful for programmatically solving problems. A good example is when I asked you in lab number 5 to parse out the domain of a specific website, or the parent website of a long website. So for instance, if we wanted to fetch www.espn.com/sports/football/Cowboys, what would be a good way to parse out everything before the first slash? That's like a reasonable regular expression. Or give me everything between 2 slashes. Get sports and football. Parse out everything between slashes. Use that as a separator. Give me the objects among slashes. So those are the types of questions that you'd want to answer using regex. And it's a really great and a powerful tool. But certainly the syntax takes some getting used to, and certainly does require you to get involved with trying to play with the libraries a little bit. So it's a little hands-on. Any questions about regular expressions and how and when you would use them? Okay. Any questions whatsoever? Is there anybody that needs clarification on anything? I'm happy to stay online for a little while and answer questions. You're also welcome to message me directly in the Zoom group chat. There's an option to message privately. You can certainly message me privately. Or you can shoot me an email. Srinath and I can help you solve problems. Again, it's a crazy time in the world. We're doing our best. If you need any help beyond just the class, let me know. I'm happy to see what I can do. And any of you that are struggling with finding internships and work, just keep your head up. I know it's a challenging time, and it's probably pretty stressful for many of you. It's stressful for me, certainly. If you need someone to talk to, just let me know, and I'm happy to help. Okay. For those of you that don't have any questions, you are more than welcome to hop off. Thank you for your time, and thank you for staying a half hour later than the class usually runs. I should be on time next week. Hopefully, as long as my business is not doing crazy stuff like it was doing today. Otherwise, have a great rest of your week, and I'll start to have assignments back to you in the next couple days. Thanks, and have a good evening if I don't talk to you.